Polling is often used for dealing with input and output. Polling is also called polled I/O or software-driven I/O. When the microcontroller repeatedly checks for the readiness of an I/O device and in between returns to a different task, then we call this polling. If the different task involves just waiting for readiness by wasting CPU cycles, then we also refer to this type of polling as busy waiting. Polling is generally not as efficient as the alternative to polling, interrupt-driven I/O. Polling is, however, simpler and doesn't require any extra hardware support. Let's now look at a simulator, a microcontroller simulator, and simulate a polling loop. In this example here, I've written a short, very simple program to poll port A, and connected to port A is a set of switches S0 to S7. Now the program begins with an initialization instruction, which basically will configure the port as an input port before we enter the actual polling loop itself. So I'm going to single step through this program by pressing the S button here, and you should see what happens as we go along. Right, the first instruction, that's this one here, move W hexadecimal FF, moves 8 ones into the W register. And the next instruction, which is the one that's highlighted here, that's just about to be executed, is when I press the single step key, that executes this instruction, and that actually moves the FF into tris A. By moving FF into tris A, we are configuring the 8 bits of the port A register as inputs. We now enter the polling route proper, which is labelled beginning with the label start, and you'll see that the first instruction moves the contents of the port A into the W register. So we've moved the port A number 0111111 because of the configuration of these switches at the moment. Okay, the polling loop then goes through a series of no operation instructions, which are just before entering a jump instruction and going back to the top of the loop. Now this type of polling loop is called busy waiting. Some people would distinguish busy waiting as a special type of polling, but I'm just going to call it polling like any other polling loop. So we keep going back and reading port A over and over again. The time this takes to go back and read port A depends on how many of these no operation instructions that we have. And also it depends on the speed of the clock. If the clock was running at 1 Hertz, for example, each one of these would give us a 1 second delay before we go back to the beginning of the loop and read the port. So you can adjust the number of no operation instructions, and depending on the clock speed, we can create a time delay between reading the port. Now, before we go back and read go back to the top of the loop this time, I'm going to just change one of these switch settings, or a couple of these switch settings, just to show you that if during the waiting cycle the switch configuration changes, then when we come back to reading port A again, we'll read the new switch combination and copy that into the W register. Okay, so this isn't doing anything particularly useful, this program, because obviously when we read the port and find something that's changed, we need to go and store it somewhere or process it in some way. But we've left that out deliberately just so we can focus on the key aspect of a polling loop.